this meeting. Go for a couple seconds.
Guys, let's get on out. Yes, please. Oh, it's not down.
Starts recording.
Okay. Well, thank you all for coming to this momentous occasion. I'd like to say, I want to say it's a long time coming, but it's a long time coming. So we're here for the defense of, Masters defense of Jeremy Laux, who all of you know, all of you know. And he has his bachelor's degree in geology from our department and is now striving to get his master's degree. So the procedure we normally follow is that he'll give a presentation of about 25 minutes. And at the end of that, we'll open it up for questions from everyone pertaining to the presentation topic. And then we'll let those go for just a short amount of time. This time we have a compressed schedule, mostly because of my schedule. I apologize for that. Then we'll excuse you, and then the committee will deliberate more thoroughly with that. Jeremy has done a lot of things for the department. He was very dependable. He's done a lot for the university. I'm sure every one of you that's dressed in stripes knows all about that. And we're really proud of that aspect of him. But we're also proud that he's going to finish. And so I'll turn it over to you.
Actually be a geologist and things of that nature. All right, well, I'll just throw this bad boy up. Well, as John said, I am Jeremy Laux. I'm here to present my work for my master's degree, and my paper is titled The Impact of Antecedent Groundwater Heads and Transient Aquifer Storage on Flood Peak Attenuation in an Unconfined Karst Aquifer, the Study of the Upper Suwannee River, Florida, USA. Just a quick layout. I'm going to be talking about an introduction, basically what we were looking for, what problems we had that we wanted to understand better. Brief overview of the study area and the geology, the methodology, the way I got my data, the way the data was analyzed, results, obviously, what we found, and then a discussion, basically the pertinent, what is important about what we did, what did we discover, what can we learn from the work that was done here. Okay, just a brief introduction. Flood peak prediction is flawed in basins that have flood peak attenuation. Now, flood peak attenuation means you have flood peaks, you have floods that are building and building, and something in the environment, usually an aquifer or spillage or some sort of situation, causes the flood peak to be less than you would expect based on normal circumstances. This can be due to storage effects, this can be due to overflow of the banks, but you will get less water downstream than you expect to in a normal situation. Because in this situation, we get a disconnect between runoff and discharge. Normally, runoff goes over the land, directly into the river, into tributaries, which then build the height that I just mentioned. But in this case, these basins that have flood peak attenuation, there is some sort of disconnect. There is some sort of way that the floodwaters are not building the way that you would expect them to. In this particular situation, groundwater and surface water interaction, so losing water to the ground, to the aquifer, can affect this discharge very quickly due to a few factors, which I will discuss as we go through this. Another thing we wanted to look at was the National Weather Service. They issue flood warnings, and in basins where you have peak attenuation, they can be inaccurate due to these groundwater and surface water interactions. These warnings cost people money, and you get lots of low confidence. If your weatherman says, oh, it's going to be sunny today, and you look outside here and it's snowing, well, obviously you're not going to trust them as much, and that is a problem. One other thing we wanted to look at was to gain a better understanding of the conditions that actually lead to spring reversals and to pollution issues in unconfined karst systems. Quick overview of the Suwannee Basin geology here. The Suwannee River starts in southern Georgia and flows through over the Cody Scarp. It's kind of hard to tell on this, but it goes with my black line there, right through that, where Ellaville, Louisville, Brantford, and end up in the Gulf of Mexico. Now, in the northern section, above that black line, it is over a confined aquifer where runoff goes directly into the river. It's not absorbed very heavily, and stream building and flood peaks are considered normal for rivers. However, it crosses the Cody Scarp, which is kind of a geologic boundary between the upper and the lower basins, and it becomes into an unconfined aquifer, which means that water flows directly from the surface, sinks into the ground and into the aquifer directly. There's no confining layer. There's nothing that prevents it. And so this is an important aspect for our situation because we get all this flood water coming from Georgia, from northern Florida, crosses the Cody Scarp. It all runs through Ellaville, and then between Ellaville and Brantford, it's an 84-kilometer stretch with no tributaries, no other surface water. It's a karst environment, which is sinkholes, caverns, springs, things of that nature. And so we have this uninterrupted 84-kilometer stretch to study the effects of attenuation. The Suwannee and Ocala limestones are the primary units of the Upper Floridian aquifer. They are very heavily eroded. They're high porosity and permeability rocks, which allow for water to move very quickly throughout. There are also numerous springs. There's, I believe, over 20 springs between Lureville and Brantford. Now, the reason, apparently I've filled up the meeting. Sorry, people. Is that popping up on there? Yes. That's the problem. I apologize.
There's a don't show again.
Okay, thank you. All right, so we looked at 3 river gauges. We were looking at river discharge and stage height, and we looked at Ellaville, Lureville, and Brantford, Lureville being basically halfway between them. We didn't use it in most of our results, but it was a nice measure there. Brantford being the downstream right before another tributary, the Santa Fe River, and enters the Suwannee River. We also looked at well data as a proxy for groundwater elevations, and that was just upstream of Brantford, about 9 kilometers, but we had it pretty tied in. All right, just a quick overview on some methods, data collection. The river gauges were USGS river gauges. They took an average of 1 reading per day was averaged for height and discharge, and those were again at Ellaville, Lureville, and Brantford. We also calculated a discharge ratio of Ellaville to Brantford, so upstream divided by downstream. And I'll explain a little more about that and why that's important in a bit. We also got well data from the Suwannee River Water Management District by Brantford, and that was a bit more difficult. That the period of data recording would be completely random sometimes, one a week or 1 in 3 years. So we had some issues with that, which helped cause some trouble with our results later. Also, the National Weather Service issued warnings, and so I was able to use an Iowa State website to go through and actually cross-reference all of the flood events that I identified with warnings at Ellaville and Brantford, and we ended up using the ones for Brantford for this discussion. And here we go. Here's the big graph, obviously. So this is a graph of river discharge over an 11-year period from January of 2003 to December 31st of 2013. We got discharge in cubic meters per second on the left and the data on the bottom. Some things to look at here. I have the Ellaville and Brantford gauges, and we decided that we would have a cutoff at about 300 cubic meters per second. The average discharge of the river over the period was about 110 cubic meters per second. So we decided that events over 300 were large enough to consider as floods, even though the actual flood cutoff was about 725 cubic meters per second at Brantford. This gave us 20 events overall to look at, including, you see there's a few very large ones, especially this one is April of 2009, that very large one, which reached 1,600 cubic meters per second, 16 times the base flow at its peak in Ellaville. Now we need to talk a little bit about attenuation and discharge ratio. So the discharge ratio, as I said earlier, was Ellaville divided by Brantford. If it's below 1, the flood will lose water and attenuate, which means that somewhere along the line from Ellaville to Brantford, water was lost and to the aquifer, to bank storage, and other effects, which I will describe in a bit. If it's equal to 1, there was no change, which doesn't mean that there was no attenuation, but it means that any water lost to the aquifer was then balanced by water coming in from springs and other sources. And then if it's greater than 1, the flood does not show attenuation, and therefore it actually builds like a normal flood we would expect. It would build water downstream. We had 11 main floods that we discussed, which both had well and stage data. And part of the problem, again, that I said earlier was the well data was scattered, so we didn't have as much as we wanted. We were looking at the antecedent data, which is prior to the event, the buildup. So we wanted events that had both an antecedent well and stage prior to the main flood buildup that prompted the flood stage we were looking at. So of those 11, 8 of them attenuated and 3 showed no attenuation and actually built on their discharge. When you take into account all 20, all of these had stage heights, which is a nice proxy. All of them had stage heights, and actually an equal number, 10 attenuated and 10 had no attenuation. Let me explain what attenuation is, because I've said the term a few times, and I'd like to explain it a little bit. Attenuation, meaning losing the water downstream. I have 2 floods here. This one is August of 2003, and the one on the right is March of 2013 with the discharge on the sides there. The light gray is Branford. I'm not sure how well everyone can see it, but the light gray line and both of these is Branford. In the first flood, you notice it has a higher discharge throughout the entire situation, with Ellaville, the upstream, having a lower discharge. That means that flood waters increased throughout the entire duration of that flood. So as it went downstream, there was not attenuation. It built and built until it hit a flood peak. However, the one on the right, the March 2013 flood, if you notice, Ellaville, the upstream one, has a higher flood peak than Branford. It's actually a pretty graph. It's actually kind of beautiful. But what that shows is that between the flood peak hitting in Ellaville at about 800, it lost roughly 70 cubic meters per second, which is quite a bit of water, actually, by the time it hit downstream only a few days later. So that flood attenuated. It lost a significant amount of flow. I know tables aren't usually done in these, but to me, it made sense. Just looking at the peak dates, there was no real discernible pattern on when flood peaks occurred over this 11-year period, which was something we wanted to look at. You can see which ones had well data as well as the date prior to, and then a nice little table of the discharge ratios. This whole thing is sort of a discharge ratio. So this April 09 flood, the biggest flood that we had, actually lost 26% of its flow in 84 kilometers. That's a huge amount of water that it lost. And if you look down at the bottom, August 05, that flood actually gained 21% of flow as it went downstream. So you have a nice big range. There are 4 that are selected in red, and these 4 behaved oddly compared to the rest of them, which I will discuss a bit in the discussion section, but I wanted to highlight those there. All right, another thing we were looking at, obviously, we wanted to make sure our well data, which we were using as a proxy for water table elevation, we wanted to make sure that this actually did line up with our flood results. And so we have, again, the discharge graph that I showed you earlier, but at the same time, on a second y-axis, I have the well elevations plotted. And as you can see, they actually follow pretty well the way that the discharge did. And you can see a few periods of drought, pretty heavy drought there in the middle, and then over to the right, there's a few drought periods. What you can also see is that we ran out of, there was issues with recording, we're not sure, but there was very little data from 2012 on with wells, which actually impacted a few flood events that we would have liked to use in our analysis in every way. Also, that horizontal line there is the average well elevation during the period. Okay, got some nice little plots for you. We're looking at these well elevations versus the discharge ratio. So looking at all 11 floods that had the well data, graphed them up, the discharge ratio on the y-axis and the elevation in meters on the x-axis. And you can see in the first one, there's a reasonable linear trend. It's not super strong. But if you notice, the April 09 and April 05 floods are a bit of outliers. We removed them, and again, I will discuss that in a bit, why we removed them. Removed them, and suddenly the goodness of fit jumped all the way to 0.85, which is a very positive linear trend, showing that there is a strong relationship between well elevation and the discharge ratio that we had in this situation. We also wanted to look at stage. Stage is going to be related to your water table because the Suwannee River is actually the part where all the water flows in this situation. There's very little surface water in the area, so all the groundwater flows into this. So we can also use this as a proxy, and it's a lot better because there's constant stage data versus the very scattered well data. So again, with those same 11 floods from the last one, you see there's a linear trend, but removing those 2 floods again, you get a very strong positive, again, linear trend of 0.87, showing that there's a very strong situation. Now, however, since we had stage for all the events that we discovered in this, we then graphed that. You get a pretty weak linear trend there, but it works. Again, removing those April floods and also the March 2008 that's in the bottom right there, and then a February of 2010 flood that's there, and I will again describe why in a bit. But removing those 4 floods, suddenly the R squared goes up to 0.77. So with additional data here, it still remains a strong correlation. Okay, now on to the discussion. We'll actually talk about why some of this matters. Again, the understanding transient aquifer storage, basically where the water goes and why it goes there. And also looking at the determining factors for the flood behavior, I will discuss why those 4 events were removed. Then we'll discuss the accuracy of the National Weather Service flood warnings, what we found, and if they can improve it. And then also a little bit on aquifer process implications of this research. First off, looking at transient aquifer storage. So there's 2 main kinds that we were discussing here, which is bank storage, which is storage in floodplains in the upper aquifer and also in the areas directly connected to the river. So the banks, the underneath, that general surface areas where water flows in during floods due to hydraulic gradients being reversed. And then also the aquifer matrix storage with a nice little display from one of Jason's papers. So I'll just explain that a little bit. The situation A there, you have a low river and water will flow into the river from conduits, from the groundwater, etc. The river is the end goal for all this water due to the hydraulic gradients. They flow, or they cause flow to go into the river. However, when you have a flood, the rising water in the river causes these hydraulic gradients to reverse, pressure reverses, and now you have river water displacing water in the aquifer and water in these conduits. And now in karst, conduits are basically, think of like pipes in your house. They allow water to travel deep into an aquifer and then have exchange with the actual aquifer matrix, the pure rock that makes up the storage. And these conduits being there allow it to travel very quickly and very far into aquifers. And also this, what it does is it displaces water up into the vadose zone, which is the non-saturated part of either an aquifer or soil. You have your water table, and above that is the vadose zone, which has water in it, but it's not saturated with water. And so what this does is it actually pushes the water that's already in the aquifer, pushes it up into the vadose zone. And then you have, as it's showing, it's kind of a cycle. Also what happens is, okay, the flood wave passes, water then, the pressure changes, water then flows from the aquifer back into the river, keeping it artificially high. Now this causes attenuation because water that would be in the flood, would be in the river, is then put into the aquifer and stored temporarily, which then, as the flood wave passes, it disperses farther out. So it actually keeps water at a higher level for a longer period, but it decreases the overall flood peak of the situation. So okay, we had a couple troublesome floods, and I wanted to explain why they were an issue and why they were removed. So we had the 2 big floods. It's April 2009, April 2005. By volume, at Ellaville, the April 2009 was nearly 1,600 cubic meters, which is, again, basically 16 times our standard flow. And then the April 05 one had 1,100, which is 10 times our average flow. So these are very large floods. But they lost 26% and 15% respectively to this transient storage, as well as transient storage either in the aquifer or overland. Some of these overflowed, things like that. The conditions for the 09 flood, the antecedent conditions, they actually favored attenuation, but just not to the level that occurred that we saw. Like, this was going to attenuate by the antecedent conditions, but it should not have attenuated as much as it did. Also, the April 05 flood, the antecedent factors actually favored non-attenuation. It should have gained water as it went. However, it still lost 15% of its water. So why did these attenuate? These floods were very large, and they rose faster and higher than the others, which caused a steep hydrograph, which is a graph of river discharge as it goes up and down. And this caused the hydraulic heads to change much faster in the river than the groundwater could respond to it. And therefore, overwhelmingly, the pressure difference was so much that it overwhelmingly forced the water away in the aquifer more than we would have expected because of how steep these were, how quickly and how large they were. Also, we had these March 2008 and February 2010 floods. Now, these two were not used in the analysis that also had wells. These were only stage one. This March 08 one attenuates, but it has a very high stage, drastically larger than any other flood that attenuated. Also, February 2010, it did not have attenuation, but it also had the highest antecedent stage, a very high stage height, but we expected more water to flow through. It didn't have as much as we expected. So why were these problematic? Well, both floods were the second of the month. So each of these months, March of 08 and February 2010, had two flood events in them. We had a flood peak at the beginning of the month. It went down for only 12 days, and then suddenly you had another flood peak. And we decided that these 12 days was not a long enough time for the system to recalibrate itself to get back into equilibrium. And so because the system was still in flux, it's hard to trust that data for being accurate, as you still had a lot of conflicting pressures and things like that going on. A little bit about the National Weather Service flood warning accuracy. I actually did talk to the National Weather Service about this, so they were pretty helpful. We had 5 of the floods that were large enough for warning, so over 700 cubic meters at Brantford. March 03, October 04, April 05, those April 09, those two really big ones, and then March 2013, which I showed in my attenuation slide earlier. So the accuracy was a bit varied. The first 3, the early 2000s ones, those are accurate by plus or minus 0.25 meters. That's fairly accurate for a 5-day forecast. They were doing 5-day forecasts in these. And so a few of them were just slightly over, a few were slightly under, but they were mostly accurate. However, April 2009 was off by, they over-predicted by 1.1 meters, which is quite a bit. That's quite a bit of stage height, and it can mean the difference between an evacuation and nothing. Also, March 2013 was off by nearly 2 meters. So basically my height, they were off by for the height of the river. And that's a big problem for only 5 days in advance when you have people with economics and evacuations, things like that. That's a big deal. Also, one other thing, I want to talk about some aquifer processes as well. The process that was going on that I didn't really mention too much was spring reversals in the river. So your hydraulic gradients change and water flows into the rivers. Now this river has many springs, and during normal flow, the springs flow into the river. They put groundwater into the river, keep it artificially high. However, during this reversed flow, the springs reverse direction and river water flows deep into the aquifers. It's actually an important process for aquifer health, but it's also a concern for pollution. In this case, because it's conduits, it's not flowing through grains or other things like that. It's really unfiltered and can be transported very deep into the aquifer, which then makes it very difficult to remove. And later floods or even sometimes normal flow from these springs can actually pump quite a bit of pollution from a prior event back into the river, making it very hard to remediate. Also, there are ecosystems in caves and conduits and things like that, and these reversals actually bring a lot of nutrients in that would otherwise not be in the system, and allows a lot of these environments to continue functioning. So that's actually a really cool thing, and part of the reason this is involved here is that our understanding of these floods and that helps us to understand when we expect these spring reversals to happen, which then can help us understand when pollution occurs and when nutrients are brought in. Overall conclusions here, I have shown that the antecedent groundwater heads, they do control the flood peak attenuation in the lower Suwannee River. So we have a positive linear relationship between these groundwater heads as shown by water table elevation and as shown by river stage with attenuation. And then both of those can be used to effectively model groundwater heads and to gain an estimate of how much you expect a flood to attenuate. Given upstream values at Ellaville, you should be able to estimate how much attenuation you would have downstream for Brantford. This transient aquifer storage, both the bank and matrix storage, but it allows for attenuation to occur rapidly, and that's a big deal because even in, say, a normal sediment-based river that would have attenuation for floodplains and things like that, there's a limit to how quickly that can occur and how quickly water can soak into the soil or other things. Whereas with these conduits and the high porosity and permeability of the aquifer, it allows for very, very rapid flow. And also, these flood forecasts from the National Weather Service, they do not account for these groundwater surface water interactions that occur in this basin, and therefore they're not always going to be accurate. Sometimes they can get it right, but as I've shown, sometimes they get it wrong because they're not looking into account these interactions, which are a very important part of how this system works. Got a citation from Jason's paper. I'd like to acknowledge a few people. I would like to acknowledge my committee. Jason, thank you for putting up with me and just getting me done. I really appreciate it. I'm sorry you can't be here today, but looking at the microphone for you, or the webcam, you know what I mean. I want to thank Alex for your helpful resources and keeping things in perspective for me. You really helped me out quite a few times, and I really appreciate it. And John, for not giving up on me, and for some of the help you've given me in getting things going, paperwork, things like that. I really appreciate it. I would also like to give some special shout outs to Steph, Katrina, Angela, Aaron, and my Pet Fits friends for just keeping me going and always being there and pushing me. I'd like to thank my parents and my friends back home and around the world who are watching, and I apologize, there's a bunch of you that probably tried to sign in that can't actually because we filled up the meeting, so thank you guys, that really means a lot to me. And also the Pet Band, Mitch's Misfits, and all the other groups that have supported me through all these years for getting this done. This is actually a picture of the Suwannee River. You can see how heavily eroded the limestone is, so I just want to say thank you, everyone. Are there any questions?
We have time for a few questions. I'll keep track.
Let me see if there's any. Oh, we got people clapping. I can unmute people unless Jason, if you want to unmute yourself, that'd be. Do we have any questions, guys? Anyone relevant to the topic? Anyone there? Jeremy over there. Angela.
So if you go back to
Yep.
all three of them overlaid.
All three of them overlaid. You mean this one?
Where you have one column. I've just saw the.
Yes. Okay.
You overlaid something on the well data.
Oh, yes, the well data one. This one here.
Yeah. So I noticed that the well data follows the trend very closely, but it also seems to be a little bit consistently higher than the other ones. Why is that?
Well, again, this is also you're looking at the difference in scale here. On the left one, you're running from 0 to 1,800 cubic meters per second, and on the right one, which I guess I need to minimize this. Sorry, guys. The right one is just well elevation in meters. So the disparity is a little bit more just with how that works over there. that makes any sense. They do follow it though. They have a pretty good approximation.
What Jeremy was trying to say is you can't compare the numbers.
Yeah.
Because they're different dimensions that it's measuring.
Yeah. That's what I
But
meant.
you compare the trends. Yeah. The person behind.
Patrick?
What was the process of selecting 300 cubic meters?
Cubic meters per second for the floods. Honestly, Jason and I just sat down and decided that that was a pretty reasonable. 3 times the base flow seemed like a pretty reasonable thing. Again, that was our choice. Obviously, it can be different. If we had been analyzing over 50 years, I probably would have chosen the actual flood height for what actually occurs in the river. But we needed data points, and also it was important to have those. There's still a buildup, as you can see, even in some of the smaller events here. You do get a pretty nice buildup, and so the pressures would still be being affected by the buildups and the drops as well. Kathleen had a question.
Yes. So, in your conclusion, you said that the NWS does not account for surface water, groundwater interactions, and that's why it's inaccurate, correct?
Yes.
Is there any action put in place so that the NWS does account for those interactions in the near future?
I actually talked to the head forecaster of the Southeast region. We had a nice discussion about this, and they said that they look at runoff, and they look at precipitation, and look at basin characteristics. Those are the big things that they look at, which from almost every river makes sense. Time scale is a big one for how quickly water can be absorbed into your soil, into your aquifer. There's a few things which John knows quite a bit about, but things like tortuosity and other things, how much path has to go, the permeability, other things. And so normally it's not a big deal to control for the time scale of a flood. However, due to how quickly water can move in this unconfined karst aquifer, these interactions are key to understanding how floods react in this particular situation.
So maybe along those lines, you calculated how much volume of water attenuated. And so one explanation for that attenuation is that water permeated the matrix porosity of the formations. So if you took that water and you spread it along the reach of the river where the flood occurred, how high would that water table in that matrix have to come up to absorb that water? Is it 2 meters, or is it 1/10 of a meter?
It really varies by how much. I didn't actually do any calculations to determine the height variations, part of which is because I don't have good water table data. Obviously, stage is one thing, but the relationship is there is a bit of a lag when I looked at the data between the wells and the actual stage for the same day. There would be a lag in terms of how long it would take sometimes for the overall well to step up. So I didn't actually do any analysis like that, but it is a possibility, and actually would be a good continuation of this project actually to look at the actual how much it moves in a short period of time. But you would require more constant testing than what I was given. And this is all this data was online. I've never actually been to Florida, as some of you know. I wish, but.
You mentioned in a couple of those floods that you excluded them because they were so close to this flood that was reported.
Yes.
In those particular floods, would you expect the National Weather Service predictions to be accurate, or would there still be groundwater, surface water interactions that would need to be studied to make for accurate predictions?
Yeah, they would still need to be studied, but luckily those two were not gigantic by any means in terms of discharge. February 10 had a pretty good discharge, but let me see if I can pull up the big one again. Yeah. 08 wasn't, it's a pretty large one, but 10 wasn't a pretty large one. There should be some more interaction. They just had these 2 very close peaks. It's actually hard to tell on this because of how close they are. It looks like 1 peak, but there's actually 2 in both of those. So it is something that would still need to be looked at, but it was a little bit beyond the scale of what we were doing here.
I mean, one more question.
I don't know if we have time, just a quick question about the flood events. I know up here in the streams, I would even say like the vast majority of flood events are due to snowmelt and runoff, but I was noticing that most of the flood events that you have on there are also in the spring, and I'm
Yes.
wondering if that was just due to precipitation differences.
Well, I
per
mean,
time of year.
part of this is it's Florida, so they don't really get snow. They do get water, and actually some of these larger events were from tropical storms and hurricanes, actually, that were lined up. So that's one of these where there have been a lot of tropical storms over the years, and a few of these were hurricanes that were just dumping heavily. What's very interesting is that it has to dump in a specific location, because most of Florida can get water, and you won't get a lot of flooding in the Swanee. It has to be dumped up in southern Georgia, where actually the flow gets run off and builds there. That's where the big floods actually occur. It's not when the rain is in Florida, when the rain is in Georgia and actually flows downstream.
Okay, well, thanks again, Jeremy. And
Thank you, everyone.
feel free to grab some food on your way out. The committee won't eat it at all.